Okay, guys. Thanks for being patient with me. So here we are, Physics 1112. We're looking at 21, Chapter 21, excuse me, Section 3. And we're going to talk about Kirchhoff's rules. A couple of things. Kirchhoff is how you would pronounce it in German, which Gustav Kirchhoff, who worked in the 1800s in Germany, was German, I guess. I didn't know that. Anyway, I looked up how to pronounce it because I've always said Kirchhoff because that's how I learned it was said. And that's how we say it in the United States, I guess, or in English. It's Kirchhoff's rules in English and Kirchhoff in German. So you pick your favorite language to do that in. Anyway, so he did the work and came up with these things, and everybody's happy about it. I want to say one thing first. Here up in this section here, it says these rules come from the conservation of energy and the conservation of charge. The conservation of charge is also conservation of energy when you break it down. So it really all stems from the conservation of energy. However, we're not going to distinguish between charge and energy. So we need both. Okay, so this circuit right here that we see is it's one that requires these rules to get the equations allowing us to find everything about the circuit. We could be given currents, we could be given resistances, we could be given the EMFs, we could be given all kinds of stuff, and then there will still be things that we don't know or we aren't given. And we're going to need to use these rules to figure out what those other things are. So it's definitely doable. And Kirchhoff gave us a whole bunch of neat ways of doing it. So the first rule that we have is the junction rule. So let's highlight that, the junction rule. So we have two junctions on this circuit. We've got point A and point E. And all the currents going into point E, for example, must equal all the currents going away from or out of that point. So if you look, I've just drawn, because currents flow from the positive to the negative, I've taken the current on this R3 to be I3, and I've taken the current of R2 to be I2, and it's going, because these are driving, the EMFs are driving the circuit, then they're going to push from the positive to the negative. Okay, so that's why I'm pushing I2 in this way. Okay, so if we look, I3 is going into point E. We look and we can see I2 is going into point E. And we can look across R1, notice that I1 is going away from point E. So that gives us an equation. We get an equation of I2 plus I3 equals I1. Okay? So, great. Let's do the same thing for point A. So this is point E. Point A gives us I1 equals I2 plus I3. So what do you know? We have the same equation, and we didn't learn anything by looking at the two junctions. They both give us the same. It's because it's a simple circuit, and there will be circuits, maybe you won't see them, but there are circuits out there that are quite complicated that the junction rule really helps, okay? But we are left with one equation that works from the junction rule regarding this circuit. The second rule is the loop rule. And the loop rule says if I do a loop, I'm going to do a loop inside here. I'm going to start at A, and I'm going to go all the way around and come back to B, or to A. In fact, if you look in the book, this is point B, this is point C, this is point D, F, E, F, H, E, F, G. What? Oh, where's that? Where is that thing? Where's that darn thing? E, F, G, and H. E, F, G, H, and I. Okay, good. E, F, G, and H. Okay. All right, the loop rule. We're going to be doing a loop of A to B to C to D to E and then back to A. Okay? And the loop rule, okay, first of all, when I was talking about conservation of energy and conservation of charge, the junction rule comes from the conservation of charge. Because all the charges flowing in to a certain thing have to be equal to the charges flowing out, okay? So that's a conservation of charge situation, and totally works. This loop rule is a conservation of energy rule. So we are going to be figuring out the voltages, okay, across all of the different points and adding those voltages up. And in the end, all of those voltages, when we go around in the loop, should give us 0, okay? So that's how the loop rule works. Let's do it. We've got, okay, so it's a little confusing, all right? So let's keep it simple and straight. We're starting at A. The first, and we're going to B. The first thing that we're going to notice is we've got R2. So R2. I2 goes across R2, that's the voltage. Okay. And is it positive or negative? Okay, so we've drawn our I2 as going this way across it. And I might be wrong about that, but it doesn't matter. In the end, we'll get a positive or a negative I2. If it ends up being a negative I2, then I drew the arrows wrong, okay? If it ends up being positive, then I drew them correctly. However, what is happening as we go from A to B? Are we go with I2 in the same direction? We are losing that voltage. We're dropping down across that voltage. So that is a negative I2 R2 because we are going across it and as we do, we lose the current times the resistance voltage. Okay, so that is the voltage across R2, and it's negative. Okay, then we're going to get to epsilon, or our EMF 1. So between B and C, that is our EMF 1. We're adding it, and we are adding because it is taking us from a negative to a positive. So we're going from a low to a high, and that means that this is a positive situation. So go to figure 21.24, and you'll notice that when you do 2 points across an EMF, here's our positive side, here's our negative side. When you do it this way, your delta, if we say this is point A and this is point B, your delta V equals VB minus VA. This guy is smaller. I didn't want to do that. Let's see. No matter what happens, VA is smaller. VA is smaller than VB. Okay, so this gives us a positive. Okay, and that's exactly what we're doing when we are going in this direction around the loop. We're going across that in a positive way. So there's our positive E1. Okay, I'm going to erase this, and we'll come back and I'll draw it again when we do the other loop. So then we're going to go, we're going to do another drop. So we're going to do another drop across I2. Across R1, the internal resistance 1. So we've got our I2 times R1. Okay, and then we're going to come across to point E. Fine, everything's good. We're going to turn the corner. We're now in a I1 situation. So we've got I1, and we think that it's going to the left. So it's going to drop another, this is I1, R1. That drops more voltage, and then we're left with 0 because we're back at A. Okay, and that's how many pieces of equipment we have along the way. We've got R2, we've got EMF 1, we've got our internal resistance 1, and then we've got the main resistor R1. So that's our 4 things. 1, 2, 3, 4. We've done it. That's one loop. Let's do the other loop where we go. We're going to go from A to E, and then F, G, H, and back to A. Okay, that loop is going to look like positive I1, R1. It's positive because we're going up the stream. So instead of taking energy away from, we're going in this direction. Instead of taking energy away from the circuit, I is working in reverse, and so it's adding voltage to our Kirchhoff law. Okay? I3 across R3. It is also going against our Kirchhoff's law. So we're going to add I3, R3. Across R2, same, but it's now I3 still, and then our internal resistance 2. Then we have our EMF, but we're going in the reverse direction across the EMF. So we have to subtract off E2. Then that takes us back up to A. And we have our other 4 things that we have done. Okay? Now we can get into the algebra of all of that after. These are just the rules, and I'm just explaining the rules to you. So the other rule, when we're going this way, so here we are, we've got our point A, and we're doing this, and we're going to point B. So here's our minus, here's our plus, here's our EMF. Delta V is equal to VB minus VA. But in this case, and that equals our EMF, VA is greater than VB, meaning that this EMF has to be negative. Okay? So because we went this way across that EMF, we had to make it negative. Okay? So this is it. That's it. That's the basics. But if you notice, we just developed an equation. We've got this equation. We've got this equation. So that's 3 equations. And maybe we know all the resistances and all the EMFs, but we don't know any of the currents. We have 3 equations and 3 unknowns. There's one more loop that is important to learn, okay? Because sometimes you'll have a situation where you have 4 unknowns, okay? Or there's more unknowns than you have equations, and you need another equation. Well, there is. Here's the 3rd loop. So we've done, this is loop 1, this is loop 2. The 3rd loop is this loop. Okay? So we would start at A, we would go all the way around back to A. Let's see what that gives us for an equation. So this is loop 1, loop 2, and here's loop 3. All right, so the first thing is loop 1 is going to take us all the way around the same way. So I2, R2 plus epsilon 1 minus I2 internal resistance 1. But it doesn't take us down the middle, so we can't use that term. But we do go to this term, and we continue in the same direction. So we're going to add I1, R1. We're going to, I'm sorry, we don't ever cross R1. So that did not happen. We go to I3, R3. So I3, R3 plus I3 internal resistance 2, and then we're going to subtract off our second EMF. Okay, and all of that equals 0. Okay, so there's our technically 4 equations. Okay? And they'll help us solve for all the goodies. All right. What's next? Okay. I just want to do one other thing. I want to just remind you guys the junction rule is the conservation of charge. The loop rule is found through the conservation of energy. All right. So why are we doing it? Okay, you kind of already get it. They're purely there. The rules are there to give us methods for equations to find unknowns in circuits. Okay? And what is it that we have to do? We have to label the circuit with our there are 2 things. So, one, the junction rule. We have to label the circuit with our estimate of current direction. So we say, we think, so this is the junction rule. So we think that the current is going to go this way. So let's just look at R2. We think it's going to go this direction, okay? So if we had drawn it the other way, that's fine. It may turn out that that was correct or it's wrong or I don't know, but it doesn't matter. Whichever choice we make there, it will show up if we get the positive or negative current. We just have to be consistent. So I can't make I2 go this way across R2 and then not go this same direction across our internal resistance R1. They have to be consistent, okay? So if I say R2 gets I2 going this way across it, then of course I have to be consistent with R1 and keep it going through, okay? So into the junction E, I2 goes in there, okay? If I choose I1 to go across R1 and I say it's going this way to the left, then if I end up finding that I1 is negative and I've done all my math having it go that direction, then I was wrong. And it's okay. You just say, okay, it actually flowed the other direction. Okay? So the first thing we have to do is label the circuit with our estimate of current directions. And then the second thing, for the loop rule, we have to label the circuit with our direction of loop. Okay, what does that mean? I drew our loops. We've got loop 1 here. Okay, with a little 1 in it. We've got loop 2 going here, going in that direction, and then we've got loop 3 going there. Okay, I said which direction I want those loops to go, and then I figured these positive and negative signs accordingly. Okay, if I'm wrong, then I'm off by -1 all the way around. Okay, and the whole thing would be -1 times 0. So it doesn't matter whether you're choosing one direction or the other, you're going to get the same answers. Okay, so you can choose your loops any way you want. You can go backwards one way and forward the other way, counterclockwise at times, clockwise. It doesn't matter. As long as you label them and stick to it, okay? Label it and stick with it, and you'll get the right answers. So, that's pretty much it there. Let me talk a little bit more about when you're going across a resistor. And here we go. Here's a resistor. We're going to say that the current is going in this direction. This is, who knows, resistance I, whatever. Okay. If we've got this is B and this is A, and delta V equals VB minus VA, if VB is greater than VA, what does that mean? That means that the current really, this is a positive and this is a negative, the current really is going in that direction, okay? So what do we have in that situation? We have that delta V is equal to minus IR, okay? If we do the same thing, we've got B here and A there, RI, but we're choosing I now to go this direction. Same situation, VB is larger than VA. Then delta V equals IR, okay? The I is positive. Now, why, when we do our loop rule, do we flip them and make this one negative and this one positive? Okay, why is that? So, we know for a fact that this current is going this direction if VB is larger than VA, okay? So we're going that way current-wise. What are we doing, though? We have a voltage drop. So when we go to add and subtract voltages, a voltage drop gets negative IR. Okay, that's a voltage drop. What do we have here? I'm sorry, with the Kirchhoff second rule. I'm talking about the second rule now, okay? So let's say that we've drawn our circuit such that our loop such that we come this way across that circuit. So we've drawn our loop like this, and we're going to come through and go across like that. It has to be a negative because we are dropping. It's a voltage drop. Now, on this one over here, let's do the same thing. We're coming the same way across that. However, if we're going across it that way, we're saying that we think the current is going in the other direction. So if the current is going in the other direction, this is not a voltage drop, but a voltage increase. So we have to add IR, okay, or I sub R sub I. Okay, I hope that makes sense when you're doing the, this is not a volt, this is a, what, I'm sorry guys, I'm still under the weather a little bit. This is a voltage increase, okay, and this is a voltage drop. So when the voltage is considered to be going against the flow, which it is in this situation, that's what we're doing. Our loop is going against the current flow, okay? Our loop, current flow, opposite to each other, we get a positive. Here's our current flow right here. Here's our loop. They're in the same direction. We've got a voltage drop across IR. Okay. Next, we have our EMFs. So here's our negative, here's our positive. There's our EMF. We've got point A, we've got point B. We can go like this with our loop, right? We're going to go like that. And if we do that, then what are we going to do? We're going to end up with the current going in the wrong direction. This EMF has to be a negative EMF, okay? If we are going this way, oh boy, same EMF, plus and negative, B and A, but our loop is going that direction. That gives us a positive EMF because this is definitely a volt increase in this direction, and this is a voltage drop in that direction. Okay, and that's how you do the loop rules. And the junction rule is pretty simple. I think the junction rule is the simplest of all of them. If you guys want me to do it again, I'll do it. Here we have a junction. We've got, in fact, we can do 4. We can have I1 coming in there. We can have I2 coming in there. We can have I3. And then one of them has to be leaving. So let's do I4 as leaving. Okay? And that's a totally valid thing. And then our junction rule would just be everything that's going into this point has to equal everything that's going out of this point, this is the only one. So I4 has to equal I1 plus I2 plus I3. Okay, that's the easy one of the two loops. That's the easy one. Okay, I'd ask you guys how many questions you have at this point, and it would probably be a lot. And I'm sorry that I'm not there, but we're going to do an example. So, example 21.5 in the book. It's the exact same circuit. So let's draw it out, but this time I'm going to draw it a little bit bigger so we can do some things. Okay, there's EMF 1. There's our R1. We're going to come down here to point E. We've got this resistor. And we're going to come down here, and then we've got internal resistance R2. Okay, I believe this one was R3, this is R1, and this is R2. And you typically want to draw labels on the outside of your circuit. So let me write this as R2. Okay, I think that does it. EMF 2. All right, so we're saying, first of all, that the current is going across R1 in this direction. I'm just labeling them the way that they did in the book. We're choosing I2 to correspond with R2, and we're choosing I3 to correspond with R3, but that means that I2, it's not going to change all the way around this circuit. It's not going to change. So I2 also cuts across this guy, and it comes down here, and it flows into point E. Same thing goes for I3. And I3 must leave point A. Okay, and then we can label the points A, B, C, D, E, F, G, and H. Okay. I've done one loop. I'm going to do another loop like that. That's our second loop. And then we can do our third loop on the outside, okay, starting at A and coming back to A. That would be our loop 3, okay? So that's our outside loop, if we want to do it like that. Okay, so that's loop 3. All right, golden. Now let's write down what we know about all these resistances. and all the stuff that we do know. So we've got R1, 6.0 ohms. R2 is equal to 2.5 ohms. R3, that's equal to 1.5 ohms. R1, internal resistance 1, that's 5 ohms, 0.5 ohms. Internal resistance 2, also 0.5 ohms. That's nice. EMF 1. EMF 1 is 18 volts. And EMF 2 is 45 volts. Okay, so far so good, everyone. Let's first apply the junction rule. We did it before, and we'll do it again. We can do it at points A or E. It doesn't matter. We're gonna get the same. We're gonna get the same equation. So I'm gonna write I1 equals, and I'm doing it at A. So I1 going in equals the 2 going out, which is I2 plus I3. If you guys don't, you should see, that should be pretty obvious. Okay. That's fine. Now we need loop 1. So we're going to do our next equation. So this is equation 1. Loop 1 will give us equation 2. And we kind of already wrote down what loop 1 was. I'm going to do it again. So we have a voltage drop across I2, R2. We have a voltage increase because EMF 1 is increasing. Okay, let's do it so we can kind of see both things at the same time. So we've got EMF 1, we're increasing our voltage. We're going from a negative up to a positive. Negative up to a positive. So we've increased our voltage. We drop across R2. So that's why we've got a negative sign in front of I2, R2. And we're going to have a negative sign in front of I2 internal resistance 1 as well. And then we have to come back home. We're making it around the bend past point E. R1, I1 has to be also negative because it's a voltage drop because we're going with the current. And that all equals 0. So let's go down here and solve this thing. At least make it a nice equation to work with. So here we go. We've got epsilon 1. We're going to subtract off I1, R1. And then we're going to subtract off I2. But I2 is, I'm factoring out I2 from R1 and R2. So I'm factoring out negative I2 on those guys. That equals that. Now we can put in what the EMFs are and the other values. We don't know what I1 is, but we know what R1 is, and that's 6. And we don't know what I2 is, but R2 plus R1 is 2.5 plus 0.5, that's 3. So 3, and that equals 0. Let's rewrite that so that it's easy to see. 18 minus 6 I1 minus 3I2 equals 0. Okay. Blah, blah, blah. We got to do that for, oh, by the way, this is our equation 2. Okay. We're going to do the same thing for loop 2. I'm not going to mess around a whole bunch. You guys should do it as well, but you should find that you have I1R1 plus I3R3 plus I3 little r2 minus epsilon 2, and that equals 0. Plug in all the numbers and everything, and you should get 2I3 plus 6I1 minus 45 equals 0. And of course, all of that is in volts, right? That's the unit. Doesn't matter. We're going to end up getting our currents out of it, and that'll be in amps. So loop 3 actually is the most helpful because we skip I1 and we're left with nothing but I2 and I3, and that actually is more helpful, believe it or not. So I'm going to write out what you should get if you go in the direction that I laid out up there. You should get I2R2 plus epsilon 1 minus I2R1 plus I3, and I'm going to just shorten this up a little bit, R3 plus R2, and minus epsilon 2, EMF 2. And that should equal 0. And we're going to put in all the numbers for that and leave it up to you guys as an exercise, but 2I3 minus 3I2 minus 27 equals 0. And that is yet another equation that we can use, and it's actually a very helpful one. That's very helpful. So let's write down I1 equals I2 plus I3 down here. I1 equals I2 plus I3 from our one junction. And now we have our 4 equations. We only have 3 unknowns, but we've got our 4 equations, and that's okay. We'll figure it out. Okay, so we've got all of those guys written down nice and neat. Let's combine equations 1 and 2. And essentially what I'm doing then is taking I2 and 3 and substituting it in for this I1 right here. Okay? So here we go. We've got 18 minus 6 times I2 plus I3 instead of I1. And we're going to subtract off 3 I2s, and that all equals 0. And then to get another equation, sorry about that. from here, let's do a little algebra and solve. Let's solve this for I3, okay, in terms of I2. So if we solve this for I3 in terms of I2, let's just do that. So we've got 18 minus 6I2 plus, minus 6I3 minus 3I2 equals 0. We have 18 minus 9I2s minus 6I3s. And that equals 0. We'll say that 6I3s equals 18 minus 9I2s. And so now I3 is equal to 18 divided by 6 is 3. 9 over 6 ends up being 3/2. So we're there. And now we can take this equation and we can run that I3 right in there and solve for I2. So that's what we're going to do. We're going to insert that into equation 4. So now we have 2 times 3 minus 3 over 2 I2 minus 3 I2 minus 27 equals 0. Two times 3 is 6. 3/2 times 2 is 3 I2s minus 3 I2s minus 27 equals 0. Let's flip everything to the other side that is I2 related, and we'll get a positive 6 I2s equals 6 minus 27, which really means minus 21. I2 equals minus 21 over 6 amps. And 21 over 6 amps is 3.5 because 6 goes into 18 3 times, and then you have 3 left over, which that's a half of a 6, so 3.5 amps. Okay? But it's negative. What does that mean? It means that we chose incorrectly our I2. So let's come back up here. We chose I2 going this way. We chose it to be going this way, in this direction, and guess what? It isn't. It's going in the other direction. And I think it has to do with the fact that this EMF down here, this EMF2, is so much bigger than EMF1 up here that it's altering which direction these currents are flowing. So that's okay. We're okay. We have the answer. We know what we want. We've got this thing that says I2 is equal to 3.5 amps. Now we can figure out what I3 is real quick. I3 is equal to 3 minus 3 halves of 3.5. What is that? Where's my calculator at when I need it so much? Okay. 3 enter 2 divide times 3.5. 5.25. 5.25 amps. Three minus 5.25 amps. But it's minus a minus, so that's really a plus. And so we got I3, we got the current for I3 correct, and that kind of makes sense. 5 plus 3 is 8, so 8.25 amps is I3. Let's look at why we got I3 correct. The main driving force is E2, right? Because E2, if we look right here, compared to 18, it's 45. So you know it's pressing this way, its current. There's no doubt about I3 going like this, okay? So having our choice here be correct makes a lot of sense. So that's one good thing. We've checked on that. And we can come back down and say I3 is equal to this. And now we're left with what is I1. Well, we know that one equation where I1 is equal to I2 plus I3. I1 equals I2, which is minus 3.5 amps. Okay, it's still in the same direction because we have to be consistent. So in our consistency, we have to keep that negative for the time being, okay? Even though we know that it's a positive current going in the other direction, but our equations were derived showing it in that direction, so we have to keep with it. So then I3 is 8.25 positive. That leaves us with I1 equal to 4.75. That's 4.75 amps. So, and that is what we were looking for. We wanted to find I2, I1, and I3, and we did it, okay? And we used Kirchhoff's laws to do it. Good old Kirchhoff. Okay, I think that does it for this video. I'm going to upload it right now. Bye.